The gold in your wedding ring, the platinum in your phone, the uranium that can power a city. Where did these heaviest, most precious elements come from? They were not born in the heart of an ordinary star, the way the carbon in your body or the oxygen you breathe were. Their birthplace was something far more extreme. They were forged in a cosmic cataclysm so rare and so violent, it tears the very fabric of reality. An explosion so bright it can outshine entire galaxies, but which lasts for only a few days. This is the story of a kilonova, the collision of two stellar ghosts. To understand this explosion, we first have to meet its creators, neutron stars. These are not stars in the way we think of our sun, warm and bright. They are the collapsed zombie corpses of truly massive stars that lived fast and died in titanic explosions called supernovas. Imagine taking our entire sun, a star so large you could fit more than 1 million Earths inside it, and crushing it down, and down, and down, until all that mass is packed into a sphere no larger than a city. A single teaspoon of a neutron star would weigh billions of tons. This is matter at the absolute edge of existence, just shy of collapsing into a black hole. Now, picture two of these city-sized stellar corpses, locked in a gravitational embrace. They are spinning around each other, faster and faster, hundreds of times every single second. This isn't a calm, predictable orbit like the Earth going around the Sun. This is a frantic, tightening dance. They begin millions of miles apart, but their fate is sealed. Over millions of years they draw closer, their orbital dance becoming a desperate spiral. The space between them shrinks, from the distance between planets to the distance between moons, and finally, to nothing at all. This is a countdown to an inevitable, universe-altering collision. A death spiral powered by the most fundamental forces of nature, where two of the most extreme objects in the cosmos are being dragged together toward their final, spectacular moment. So what is pulling them together? What is draining the energy from their orbit and forcing them into this final embrace? They are literally making waves in reality itself. As these two incredibly dense objects whirl around each other, their immense gravity churns the fabric of space-time, sending out ripples called gravitational waves. These are not waves of light or sound traveling through space. They are waves of space itself, stretching and squeezing everything they pass through. This constant broadcast of gravitational waves carries energy away from the two stars, causing their orbit to decay, pulling them closer and closer together in a spiral that gets faster and faster. In the final minutes, the dance becomes a frenzy. The two neutron stars are now just a few hundred miles apart, but they are moving at a significant fraction of the speed of light. The gravitational forces are so extreme, they would stretch any normal object, like a planet or even another star, into a thin strand of atoms. But these are neutron stars, the densest objects in the universe, and they hold their shape for just a moment longer. In the final moment, the space between them vanishes. The two stars, no longer perfect spheres, are stretched and distorted into teardrop shapes, their surfaces almost touching as they whip around each other at nearly the speed of light. The scene is set for an impact of unimaginable power, a collision that will not just create a flash of light, but will fundamentally change the fabric of the cosmos around it. And then they touch. The collision is instantaneous and utterly violent. This is not a gentle merging. It is a cosmic shredding. The immense gravitational pull of each star on the other, something we call tidal forces, becomes overwhelmingly powerful at this close range. These forces don't just pull the stars together, they tear them apart from the inside out. The less massive of the two stars is often ripped to shreds first, its super-dense matter pulled into a swirling, chaotic disk around its larger companion before the final impact. In that cataclysm, vast plumes of ultra-dense, neutron-rich material are flung outwards into space. This isn't a slow expansion, it's a violent ejection, with material moving at 10, 20, even 30% of the speed of light. This event is so extreme that it shakes the very fabric of space-time. The collision of two such incredibly dense objects creates a powerful shudder, a gravitational wave that expands outwards across the universe. It is a ripple in reality itself, a silent scream announcing that something of incredible cosmic significance has just occurred. And what is left at the center of this chaos? For a fleeting moment, a new, monstrous object is born. It is not quite a black hole, and it is far too massive to be a stable neutron star. We call it a hypermassive neutron star, a spinning, super-dense behemoth, rotating hundreds of times a second, barely holding itself together against the crushing force of its own gravity. Or, if the combined mass of the two original stars is great enough, the collapse is immediate and absolute. There is no temporary monster, no final struggle. The wreckage implodes in an instant, crushing down to an infinitely small point, and a brand new black hole is born into the universe, swallowing the heart of the chaos that created it. But the real story, the one that matters to us, isn't about what's left behind. It's about what was thrown out. That rapidly expanding cloud of ejected material is the key to everything. It is not normal matter. It is a super-hot, rapidly expanding soup of fundamental particles, mostly free neutrons, liberated from the cores of the dead stars. This cloud, blasting outwards from the central explosion, is a unique environment found almost nowhere else in the universe. It is incredibly dense, fantastically hot, and absolutely saturated with free-roaming neutrons. It is a perfect cosmic laboratory, primed and ready for an incredible act of creation. Think of this expanding fireball as a crucible. The conditions inside are extreme, beyond all comparison. The density, the temperature, and the sheer number of loose neutrons create a fleeting opportunity, a window of just a few seconds where the fundamental rules of matter can be pushed to their absolute limits. Inside this chaotic storm, the alchemy begins. It's a process so fast, so frantic, it's called the rapid neutron capture process, or simply the R process. In this environment, atomic nuclei are bombarded by a relentless flood of free neutrons. They are hit so hard and so fast that they don't have time to fall apart. They just absorb neutron after neutron, getting heavier and more unstable with every single impact. In less than a single second, in that unimaginable furnace, the universe performs a miracle of creation. Neutrons, freed from the crushing gravity of their parent stars, slam into atomic cores, building them up, step by step, into the heaviest, most complex elements imaginable. It is a process so fast, so violent, it makes the slow fusion inside a star seem like a gentle simmer. This is creation in a flash. And here is the most incredible part of this entire story. That cloud of freshly minted gold, platinum, and other heavy treasures did not stay there. It was blasted outwards, a shockwave of new matter hurled into the interstellar medium, the thin gas and dust between the stars. For billions of years, this precious dust journeyed across the galaxy. It mixed with vast, cold clouds of hydrogen, waiting. It was swept up in the gravity of a new generation of stars being born, becoming part of the swirling disk that would form planets. That dust is here. It is in the ground beneath our feet. The gold in a wedding ring, the platinum in medical equipment, the uranium that powers our cities, every atom was forged in the heart of a kilonova, a ghost of a long-dead star. This spectacular event is called a kilonova because of the light it produces. For several days following the collision, that expanding cloud of new elements shines with an incredible, fading light. It's not as bright as a supernova, the explosion of a massive star, but it is far, far brighter than a regular nova. But this light is special. It is not powered by fusion, like a star. It is the afterglow of cosmic alchemy. It is fueled by the radioactive decay of all those newly formed, unstable heavy elements. As their atomic hearts rearrange themselves into more stable forms, they release enormous amounts of energy. That energy heats the cloud of debris and makes the entire thing glow. We are seeing the light from the cooling embers of creation itself. And this is not just a beautiful theory. This is not just a calculation. We have seen it happen. On August 17, 2017, our relationship with the universe changed. The LIGO and Virgo observatories, our gravitational wave detectors, felt a tiny tremor in the fabric of space-time itself, the unmistakable chirp of two neutron stars spiraling into each other. The signal told us exactly where to look. And within hours, telescopes across the globe and in orbit swiveled to that one small patch of sky, 130 million light-years away. There it was. A new point of light that wasn't there before, one that glowed and then slowly faded, just as predicted. By analyzing that light, we saw the chemical fingerprints of gold and platinum, forged in that very moment. We witnessed the birth of treasure. And yet, the wonder does not end with an answer. It deepens. We have only seen one of these events up close. How often do they really happen? Are they common, or are they incredibly rare cosmic jewels? Are they the only place where these heavy elements are made, or just the most dramatic? And what is left behind? What monster is born from the union of two such extreme objects? Does every single merger immediately create a black hole, a point of infinite density from which nothing can escape? Or can something else, perhaps a supermassive, rapidly spinning neutron star, survive for a few moments or even longer? The 2017 event gave us a profound answer, but it also gave us a new universe of questions. Each of those new questions is a new invitation from the cosmos. The light and the gravitational waves from that ancient collision traveled for 130 million years to bring us a message about our own origins. It's a powerful reminder that when we look out into the deepest, darkest corners of space, we are also looking back into the deepest parts of our own history. The quest to understand these events is, and always will be, the quest to understand ourselves. But after the brilliant flash of the kilonova fades, after the gold and platinum have been cast into the cosmos, a profound question hangs in the silence. What is left at the heart of the explosion? The drama is not over. A new mysterious object now occupies the center of the stage. The answer is not always the same, and that is what makes this so fascinating. Did the two neutron stars merge to become one, even more massive neutron star, an object pushed to the very brink of existence? Or did their combined mass overwhelm everything, creating the universe's most extreme object, a brand new black hole? For a very short time, perhaps only a few hundred milliseconds, a truly strange object can be born. It's called a hypermassive neutron star. Imagine a neutron star that is technically too heavy to exist. The only thing preventing it from collapsing instantly is its incredible spin, a dizzying rotation that temporarily fights off the overwhelming crush of its own gravity. But this is a borrowed life. This state of frantic spinning is not stable. The star is radiating away energy, slowing down ever so slightly. And as it slows, the support against gravity weakens. The battle is fierce, but the outcome is decided before it even begins. Gravity will win. And then, the final, silent collapse. The hypermassive neutron star gives up its fight. In a moment that makes no sound but shakes space-time itself, the star folds inward, compressing into an infinitely small point. It vanishes from our observable universe, leaving behind only its immense gravity. That point of no return we call a black hole. Think about that. The birth of the black hole isn't always instantaneous with the merger. It can be delayed. For a fraction of a second, a star that shouldn't exist does, before surrendering to the ultimate law of the cosmos, a delayed echo to the main event. So how can we possibly tell which fate befell the merger? We look for the afterglow. The object at the center, whether it's a stable neutron star or one that is about to collapse, can have a powerful magnetic field and be spinning furiously. This combination can act like a cosmic engine. This engine can pour energy into the surrounding cloud of debris, causing it to glow brightly in X-rays and radio waves long after the kilonova's initial flash of light has faded. By watching for this specific kind of afterglow, we can deduce the nature of the object left behind. And the answer has huge consequences for the universe. The object that remains at the center plays a critical role in the final story of the elements created in the explosion. Its energy can change the cosmic recipe. A long-lived, stable neutron star might blast the ejected material with high-energy particles, altering the types and amounts of heavy elements that are formed. An immediate collapse to a black hole, on the other hand, means that central engine is switched off, and the elements form in a different way. Each kilonova we witness is a new clue to how the universe built itself.